There is a house in Denmark that hasn't used a furnace in 30 years. Not because it's connected to a special grid, not because it runs on solar panels covering every inch of the roof, not because its owners have found some modern technological workaround, because the house itself stores heat in its walls, in its floor, in the ground beneath it. Heat collected in summer, held through autumn, released slowly, quietly, through the depths of winter. No boiler, no gas line, no service contract, no monthly bill arriving in January when the temperature outside drops below zero, and every other house on the street is burning through fuel it cannot afford. Just a building that remembered warmth and gave it back when it was needed. This is not a new idea. It is not an experimental concept being tested in a university laboratory somewhere. It is a principle that builders understood centuries ago, that physicists measured and confirmed in the 20th century, that entire northern communities built their survival around for generations. And it is a principle that the modern construction industry, the energy industry, and the building code system in most of the Western world has made almost impossible to build legally today. Not because it doesn't work, because it works without generating revenue. You cannot sell a monthly heating bill to a house that stores its own heat. You cannot service a system with no moving parts. You cannot build a maintenance contract around stone and earth and water, and that is the only reason this technology feels unfamiliar. This is that story. Go back 2,000 years. The Roman hypocaust system is usually described in history books as underfloor heating, a clever, ancient luxury, something emperors used to keep their bathhouses warm. That description is technically accurate. It is also profoundly incomplete. The hypocaust was not just a heating method, it was a thermal storage system. Hot air generated by a furnace moved through channels beneath a raised stone floor. That floor, sometimes 6 inches of solid tile and concrete, absorbed the heat. It held it and released it slowly upward into the living space long after the fire itself had died down. The Romans weren't just heating a room, they were charging a battery made of stone, capable of holding thermal energy for hours, sometimes for an entire day. The principle they were exploiting is called thermal mass, and it is one of the most powerful passive building technologies ever discovered. Every material has a capacity to store heat. Some materials store very little. AER, for instance, holds almost no heat at all. Warm a room full of air, and the moment that heat source stops, the air cools within minutes. Stone is different, concrete is different, water is different. These materials absorb heat slowly and release it slowly. The technical term is specific heat capacity. It is the measurement of how much energy a material can hold per unit of mass. Water has one of the highest specific heat capacities of any common substance. It takes enormous energy to raise the temperature of water by a single degree, and once raised, it releases that energy over an extended period. This is not a subtle effect. A single cubic meter of water can store enough thermal energy to heat a small room for an entire day. A house designed around this principle, with water, stone, or earth as its thermal core, doesn't just stay warm. It becomes a heat reservoir, charging during periods of warmth and discharging slowly during periods of cold. A battery that runs on temperature difference instead of chemical reaction, and it requires no electricity to operate, no moving parts to service, no fuel to purchase. The Romans understood this intuitively. They built it into their floors, their walls, their public buildings. But the Romans were not the first. Go further back. Neolithic builders constructing passage tombs in Ireland oriented their structures to capture solar gain at specific times of year. The famous passage at Newgrange aligns precisely with the winter solstice sunrise, flooding the interior with light and heat on the shortest day of the year. Archaeologists once interpreted this as purely ceremonial. More recent thermal analysis suggests something more practical. The thick stone passage absorbed solar energy during the brief winter sunlight hours. The interior stayed measurably warmer than the external temperature, not because of fire, because of mass and orientation. 5,000 years ago, before written language, before bronze, before the wheel was in common use, builders understood that stone holds heat, and they built accordingly. Move forward to medieval Scandinavia. Viking longhouses were not primitive shelters. They were sophisticated thermal systems. Thick turf walls, sometimes 3 feet of compressed earth and grass. Earth is an extraordinary insulator. It changes temperature slowly, extremely slowly. The ground at a depth of just 6 feet maintains a nearly constant temperature year-round. In most northern climates, that temperature sits between 8 and 12 degrees Celsius, cool in summer, warm relative to outside air in winter. Viking builders placed their structures partially into hillsides. The earth surrounding the lower walls acted as a thermal buffer. It did not just insulate, it actively moderated the interior temperature, pulling excess heat out in summer, releasing stored ground warmth in winter. The longhouse didn't fight the climate, it connected to it, and through that connection, it stayed habitable in conditions that would have been lethal in a modern, thin-walled structure without active heating. Now move to the 20th century. The physics did not change, but someone finally started measuring it precisely. In the 1940s and the 1950s, researchers began documenting what they called earth-coupled heat exchange. The principle was that the stable temperature of the ground could be used as an earth reservoir, either absorbing excess heat from a building in summer or providing warmth to a building in winter. The implications were significant. A building properly connected to the thermal mass of the earth beneath it does not need to generate heat from scratch every winter morning. It draws on a reservoir that has been accumulating energy all year. In 1977, Harold Hay, an American engineer who had spent decades studying passive thermal systems, completed what became known as the Sky Theorem house in Atascadero, California. The design was radical in its simplicity. The roof held large bags of water. In winter, the bags were exposed to sunlight during the day, absorbing solar energy and warming to temperatures well above room temperature. At night, insulating panels covered the bags, and the stored heat radiated downward through the ceiling into the living space below. In summer, the process reversed. During the day, the bags were covered to block solar gain. At night, the panels opened, and the water radiated its heat to the cool night sky, cooling below room temperature. During the day, that cool mass absorbed heat from the interior. No compressor, no refrigerant, no furnace. Monitoring showed the interior temperature remained between 65 and 75 degrees Fahrenheit throughout the year, in a California climate that saw summer highs above 100 degrees and winter nights near freezing. One researcher who visited the house described standing inside on a January morning with the exterior temperature near freezing, the interior warm and steady, and no heating system operating at all. Just water on a roof. Physics doing the rest. The results were published. The technique was documented. A handful of builders in California and New Mexico began experimenting with variations. And then, almost nothing happened. Not because the system failed, because the system had no industry behind it. No manufacturer producing roof pond components. No installer network to deploy them. No trade association lobbying for code recognition. No certification pathway that allowed appraisers to assign value to a water-filled roof in a standard mortgage assessment. The insurance industry looked at bags of water on a roof and saw liability. The appraisal system looked at a house with no furnace and saw an anomaly. It had no framework to value. The building code system looked at an integrated water-filled roof and saw a category it did not recognize. Harold Hay spent the rest of his career trying to get this technique into mainstream construction. He never succeeded, not because anyone proved it did not work, because the pathway from proven physics to permitted construction runs directly through institutions that were built around a different model. A model where heat is something you purchase, where comfort is something you subscribe to, where the system that keeps you warm in January generates a bill, and that bill generates revenue, and that revenue funds the lobbying that writes the codes that determine what can be built. A house that stores its own heat from summer and releases it in winter generates none of that. It is, from the perspective of the energy economy, a threat, not to physics, to profit. Now understand what that actually means for the house you live in today. Your heating system operates on a simple and brutally inefficient principle. It takes cold air, burns fuel to heat it, and pushes it into your rooms. The rooms lose that heat to the outside within hours. The system fires again, burns more fuel, pushes more heat, and the house loses it again. It is a continuous fight against heat loss. You are not heating a building. You are constantly replacing heat that a poorly designed building cannot hold. The thermal battery house does something fundamentally different. It accumulates heat over time, days, weeks, sometimes an entire season. In mass walls, in water storage, in the earth beneath the foundation, and it releases that heat gradually at the rate the building needs it. Not in a blast that the walls immediately shed to the outside, but in a slow, steady drift that the mass controls. The difference in energy consumption between these two approaches is not marginal. Studies of earth-sheltered and high thermal mass homes consistently document heating energy reductions of 50 to 80% compared to conventional construction of equivalent size. Not 10%, not 15%, 50 to 80%. From a technology with no moving parts, no fuel requirement, no service schedule, and no monthly bill. In Part 2, we go further. We look at the specific buildings that proved this worked, and what happened to the builders who tried to bring it into the mainstream. We look at where thermal battery construction is still happening today, and why it is happening almost entirely outside the United States. And we look at the question that sits underneath all of this. If a house can store heat for days, why does your heating bill arrive every single month? The house in Taylor, South Carolina, cost $5,500 to build. No contractor, no permit complications, no elaborate mechanical system requiring annual servicing. Just a south-facing structure with 2,455 gallons of water stored in dark, painted barrels lined along the north wall. Those barrels absorb solar heat through the day. By late afternoon in winter, they are warm to the touch. By morning, they have released that warmth slowly into the space around them. No furnace fired, no propane truck arrived, no bill accumulated. A comparable heated structure would cost approximately $1,000 in fuel every single winter. The barrels didn't consult a building code before storing heat. The sun didn't wait for regulatory approval before warming the water. It just worked. Exactly the way it worked beneath a Roman hypocaust floor. Exactly the way it worked inside a Viking longhouse buried into a hillside. exactly the way Harold Hay measured it on a water-filled roof in Atascadero, California in 1977. Physics has never changed. Only the permission has. Now look at what the rest of the world did with that same physics. In Sweden, seasonal thermal energy storage is not alternative architecture, it is municipal infrastructure. Underground rock caverns, insulated and filled with water, store solar energy collected during summer months. When winter arrives, that stored heat is retrieved and distributed through district heating networks serving thousands of homes. The geology does the work. The physics does the work. The city just built around it. In Finland, similar systems operate at municipal scale. In Denmark, pit thermal energy storage projects have been expanding since the early 2010s. The EU has funded research into large-scale seasonal storage across multiple member nations because the energy math is undeniable. Heat stored in summer costs almost nothing to collect. Heat generated from fuel in winter costs everything. The gap between those two numbers is where an entire continent decided to build. In China, attached thermal mass sun spaces are described in recent published research as a popular, simple, low-cost, and widely used retrofit measure in cold northern climates. Not experimental, not niche, standard practice. Government supported, widely replicated. In Germany, passive house construction, buildings so thermally massive and so carefully sealed that body heat and appliance heat alone maintain comfortable interior temperatures through a northern European winter, has produced over 60,000 certified structures. That number represents decades of construction, thousands of builders trained in the method, a certification infrastructure that rewards thermal performance, and a mortgage system that has learned to recognize and value what it cannot always see on a standard appraisal form. America has a few hundred passive house structures. Not because American winters are less cold, not because American physics operates differently, not because American builders lack the skill, because the system surrounding construction in America was built to reward a different outcome. And that system does not easily change direction. Consider what every thermal battery house represents to the industries surrounding conventional construction. Every high thermal mass wall installed is a gas furnace never sold. Every earth-sheltered home completed is a fuel delivery route that ends permanently. Every seasonal storage system operational is a utility meter that stops accumulating charges through the coldest months of the year. The thermal battery house does not just reduce a heating bill, it threatens the business model that the heating bill funds. And that business model has representatives in every room where building codes are written. The industry did not ban thermal battery construction outright. It made the pathway narrow enough that most people never find it. Code complications, appraisal uncertainty, insurance hesitation, lender unfamiliarity. The burden of proof placed entirely on anyone proposing an alternate method, while the conventional furnace-dependent house walks a paved road with no questions asked. Each obstacle alone is manageable. Together, they form something more powerful than a ban. They form invisibility. Most people never learn this technology exists. Those who do find it nearly impossible to finance. Those who finance it struggle to permit it. Those who permit it watch it appraise poorly against comparable sales that do not include it. The knowledge did not fail. The infrastructure around it was never built, but the physics is still there. On the other side of every obstacle, unchanged, undefeated, waiting. The stone still holds heat the same way it held heat beneath a Roman floor 2,000 years ago. The water still stores energy the same way it stored energy in Harold Hayes' roof in 1977. The Earth beneath every foundation still sits at a stable temperature that neither winter nor summer can significantly disturb. These are not design preferences. They are physical constants. And physical constants do not expire because a building code fails to recognize them. The Roman architects knew it. The Viking builders knew it. Researchers at Los Alamos measured it. Builders in Germany certified it 60,000 times. The house that heats itself is not waiting for invention. It is waiting for permission. And permission, unlike physics, can change. The sun still rises every morning. The stone still remembers every afternoon. The earth beneath your feet is warmer right now than the air above it. The heat is already there. It always was.